So last time in the very end we introduced the concept of marginal quantity, marginal profit, marginal cost, and we still didn't see any example. So let's discuss an example. So we will be talking about, well, once again, business and directly some functions, cost function. And demand equation. Minimal should the company increase the price or decrease. So you can imagine, well, a story that you have a company that has, well, such and such cost function, fixed cost of 100, variable cost of this expression, 10 kilos, this variable 100. Demand equation, well, when quantity is 100, you can imagine a story, but basically you have a company which mathematically looks like this. You have demand equation, you have cost function, and well, maybe some analyst told the company, well, let's minimize the average cost. And they did, and now they have this level of production, but now they realize that the analyst was not that good. In fact, they shouldn't have minimized the average cost, they should have maximized the profit. And now they want to understand in which direction to move. Should they increase the price from here or decrease it? Okay, so for now it looks like somewhat complicated problem because we have to decide what to do. We don't exactly know how many units we are producing. We don't exactly know what is the price at this point. So maybe first let's come up with a plan. How will we approach this problem? Yeah. C of U equal to P of Q. Why would we do that? So this thing is the price. The price for which you are selling 1 unit. This thing is the cost of producing Q units. So yes, that doesn't make much sense. Find the revenue. Okay, so it might be one step. The revenue is important, but that's not exactly the most important. I mean, once again, companies are usually not that. I mean, it doesn't matter what is the revenue. What matters is the profit. So maybe finding the profit might be a good idea. But still, in the end, what should we do? I mean, I'm not asking like what kind of equation should I write just now. I'm asking what general steps we should undertake. I mean, we want to arrive at a decision. Should we increase the price or decrease the price? Yeah.
Sorry, is that a big P or a little p?
That's small p.
Okay.
So that's small p, and that's demand equation. Okay, yes, that's a good observation. I don't know at this point what is the price. So maybe it is reasonable to try to find out what is the price. Okay, so one observation is so kind of, well, let's say plan. Maybe it's a good idea to find the price. Find P, well, at what point? At this point, at this level of production, that minimizes average cost. Well, two questions related to this. It sounds directly, first of all, it sounds directly relevant to the question. On the other hand, well, suppose that you found this price. What's next? How would you answer the question? Suppose I tell you that, no, the price is, I don't know, 15. What would you do next? Again? Well, let's find P and Q. Okay, so now I tell you that the price is 15 and the quantity is 500.
You want to maximize the revenue, so you set the...
I actually don't. I don't want to maximize the revenue. I want to
And why
maximize
would
the
you?
profit.
But the cost, at the minimum cost,
Yes.
so then you have to maximize the profit. So you find the P prime of Q and set it to 0.
P prime of Q.
Set it to 0. That's the maximum. That's
So, I see. So, if you want to maximize the profit, yes, at this point, the derivative of profit relative to quantity will be 0.
yeah.
But actually, we are not talking about trying to maximize the profit. We are talking about just making a decision at this point. Our level of production is already set at this point where the average cost is minimal. And now we are trying to make a decision from here. Where should we go? Should we decrease or increase? So, I mean, in a way, you're right. One way to approach it would be, in general, find the maximum possible profit, and then we'll compare it to this level of production. That would be a strategy, but maybe not the shortest possible way to get to the answer. So maybe, yeah.
Do we find marginal cost?
Marginal cost. Okay, why would you find marginal cost? Suppose I tell you that the marginal cost is 5. What happens next?
Then you can increase or decrease the price.
Greater than 0, then you increase production.
What is greater than 0?
Oh.
I mean, the end of the sentence is right.
That's like, I'm sorry, the profit is greater than 0.
The marginal profit. So if at this point, well, suppose indeed that we already know what is price and quantity at the current level of production, at the level of production that minimizes the average cost. Well, to make a decision whether we should increase the price or decrease the price, whether we should increase the quantity or decrease the quantity, we should talk about the marginal profit. By increasing the say quantity by 1, whether the profit will be still positive from sales of this additional unit or negative. So then find the marginal profit. Find marginal profit at this level of production Q. Well, if marginal profit is positive, increase Q. If marginal profit is negative, decrease Q. So somehow it took, well, some time for us to get here, but you should realize that on the midterm there will be a problem that asks you, well, for a policy decision, and you should know that it equates to finding marginal profit and deciding whether it's positive or negative. It should be almost automatic. Well, anyway, so we want, in the end, we'll find this So our last step in the solution of the problem perhaps will be this one. Find the marginal profit at this point and, well, decide whether it's positive or negative. But we are still missing something in the plan. Well, to find this P and Q, how would we find this? Minimum of the cost. How do we find the minimum of the average cost? Yes. Okay. So Q to find Q that minimizes the average cost will solve this equation. Average cost is equal to marginal cost. In the end of last lecture, we discussed that to minimize the average cost, we should solve such an equation. Okay, now we have a kind of complete plan. Maybe let's decide on, well, what is the priority. In the end, I will do this. To get to this step, I will do this. To get here, I will do this. So I'll start here, continue here, and finally make this decision. Okay, so now let's actually start computing. Yes?
Did you find the marginal profit? What does it mean when it's bigger than zero?
So marginal profit is, well, it's the profit that you get by selling one extra unit. I mean, you produce few units, and now you are deciding, should I produce one extra unit? Well, this unit will give me a positive profit or negative profit. That's the meaning of marginal profit being positive or negative. And of course, if it is positive, well, yes, if you produce it, sell it, and get the profit. Okay, other questions so far? Yeah?
Just wondering, you find marginal profit before you do Q, right?
Yes.
But the question asks, should the company increase the price or decrease it? So
Okay, yes.
would be or
So indeed,
yeah.
our plan is still not complete. You're right.
Oh, okay.
In the fourth step, we'll see whether we should increase the quantity and, well, how change in P, in Q, so we define here, reflects in change in P. So you're absolutely right. We actually did miss a small step, and, well, you're right. So now we have even better plan. Okay, other questions about, well, the plan or the problem? So the observation was, the question was about whether we should raise the price or should increase the price or decrease. But in this step, we found out whether we should increase the quantity produced or decrease. Well, of course, quantity and price are related. So change in quantity will relate to change in price, and we'll use it to answer the actual question. Okay, so let's implement these steps. Let's start with the first step. Q that minimizes the average cost. Well, for this we solve this equation. The average cost being 100 plus 10Q plus Q squared over 100 divided by Q must be equal to the marginal cost, which is the derivative of this expression. 10 plus 2Q over 100. So we want to solve this equation. Well, let's multiply both sides by Q. 100 plus 10Q this, bring this to the right, and I get 100 is q squared over 100. So q squared is 100 squared, and q is 100. Okay, maybe simple question. Why did I write that q is 100 and not minus 100? It's quantity, of course. We should not forget that we are talking about actual business, and q is not just any number, it's quantity of some units produced. Okay. Otherwise, it was just solving this equation, so basically simple algebra. Okay, so now we know that the company currently operates at the level of production of 100 units. So we solve this part. Let's go to this part. Find, we actually just did this. Maybe we can also decide that we don't really need to know the price to go to the third step. So as we are solving, we might as well revise the plan a little bit. This price seems to be somewhat irrelevant. Because we just should find what is the profit and whether it's what is the marginal profit and what is, in this, is positive or negative. Well, to find the marginal profit, we should find the profit itself. What is the profit in general?
Revenue minus cost.
Revenue minus the cost. So it's money obtained from sales minus how much money it cost us to produce. Okay, the revenue, what is the revenue? Yes, it's how much money did we get from sales of each one of the Q units times the number of units. Okay, so if I want to express everything in terms of Q, I would write that price is, well, here it is. It's given to me by demand equation. So it's 20 minus Q over 100 times Q minus the cost, which is this thing. 100 plus 10Q plus Q squared over 100. Okay, so now I have my profit as a function of Q. On next step, I will be taking its derivative to find the marginal profit. So maybe it makes sense for me to simplify this expression first, before taking the derivative. So say that I have minus 100 plus 20Q and minus 10Q, so it's plus 10Q. Minus Q squared over 100 and minus another Q squared over 100, so minus 2Q squared over 100. Or I can write this Q squared over 50, like this. Anyway, we found the profit as a function of quantity. Now we find the marginal profit. Should be very simple, just derivative of this expression. So it is 10 minus 2 times 2Q divided by 100. Question? I mean, don't be shy. If something is wrong, it might be actually wrong. If something feels wrong, it might be actually wrong. Anyway, so we get that this is 10 minus Q over 25. Well, only now we can actually plug in what Q is. the current level of production is 100 from here. So when Q is 100, the marginal profit is n minus 100 over 25, so it is 6, and it is positive. It means, well, this means that by producing one extra unit instead of 100 units, by producing 101 units, you'll get 6 mod overs. So of course you should increase the production. So Q should be increased. Well, and as you noted, that still doesn't answer the question. We know that Q must be increased, but the question is different. Should the price be increased? So what can we say about the price? Well, we can either think a little bit by, well, if we want to sell more products, we should probably decrease the price, not increase it. Or you can actually go to this equation and see that Q in this demand equation comes with a negative sign. When Q increases, the price decreases. So this is 20 minus Q over 100 should decrease, should be decreased.
Can you explain why price should be decreasing if Q?
So, kind of intuitive explanation is that in real world business, if you want to sell more units, you should decrease the price. I mean, if you sell them cheaper, you'll sell more.
Oh, okay.
But the mathematical explanation in this particular problem, well, P and Q are related by such equation. If you make Q bigger, the difference 20 minus Q times something will become smaller.
Oh, okay.
Yeah.
So by maximizing the quantity, how Gus said, and you plug it into the MPQ equation. So from there you found out that it was positive, right? So that means that you should continue to increase your quantity?
Yes. So the question was, well, what are the implications here? The implication is, well, the marginal profit is positive, it means I should increase the quantity, well, at least by 1. How much I should increase the quantity? Well, I don't know. I should keep increasing it all the way until the marginal profit is still positive. So probably all the way until 10 minus Q over 25 is positive, or until, well, Q is 250. So in fact, if the question was about actually maximizing the profit, I would probably say, well, this is positive all the way until Q is 250, and then the maximum profit will happen when Q is 250. But that's not the question. The question is only about policy decision from that point. Should it be increased or decreased? It's not asking whether it should be increased all the way up to 200. Just should it be increased or decreased? And the answer is, well, it should be increased because by increasing it, you'll get more profit.
Can you calculate how much the quantity should be increased?
Yes, so I was saying that if you want to actually maximize the profit, you would keep increasing all the way until the marginal profit becomes negative, or 0, and then negative until Q is 200. But that's not the question.
Yeah, I'm just asking.
Yes. Yeah. So the question was, can we solve this in terms of the price? Can we approach the same question using the price and using the demand equation? And the answer is, in fact, yes. We could have expressed this profit in terms not of Q, but rather in terms of the price. And then we would find the derivative of that expression relative to price. And then the derivative would mean, well, for every increase of price by $1, will the profit increase or decrease, well, by some amount? And that, yes, that would work, and we just chose a different way. But it would work, yes. Other questions? Yeah.
But if you express marginal profit in terms of price, like what would it mean if that was greater than 0 or less than 0? Would it mean the same thing?
Okay, so maybe let me write down this reservation. So alternative plan. Guys, we are discussing another approach to the same problem, so well, it is also useful. I mean, you might come up with a different approach in some situations. So the alternative would be write the same function profit, but now as a function of the price. It is possible because we have, well, if it is a function of Q, it is automatically a function of P as well, because there is demand equation that relates P and Q. And then find, well, price corresponding to this amount Q, well, that minimizes average cost. So let's skip for a second how we actually find it. But once you found it, well, plug it into the derivative of profit with respect to the price. What is the meaning of this expression? Well, it means how much will the profit grow? Well, how much will the profit change if the price is increased by $1? So if this thing is positive, price should be increased. But of course, in this problem, it will be negative, and the price will turn out to, well, it will turn out that the price will decrease. If price should increase, okay, so any other questions about this? Yeah.
What if it says that it's operating at a higher break-even point? Should it increase
I mean, same principle of compute marginal profit.
Yeah. Because obviously after it's like
Let's not discuss it. Other questions? Yeah.
How would we find price that minimizes the
Okay, so basically, how would we find this step? Well, I would say that we don't really have any other way but doing what we already did, this finding the quantity and then plugging it into this equation. So in a way, you would take one extra step out from here, but you would add one extra step to here. So it's not simple solution, it's just alternative solution. Okay, so what can I say about this problem? It is, as formulated, it is harder than whatever you are going to get on an exam. Because, well, even though it is about all the notions that you should be familiar with, it is kind of, well, it consists of 2 or 3 smaller but very simple problems. Find the level of production minimizing the cost, find the marginal profit, find whether the company should increase or decrease production. These 3 steps are very easy, and each one of them can appear on any kind of exam, even on a quiz. But well, such a problem, well, it's a little bit more complicated. It could appear in homework, but not, well, in an actual exam. At least not in our course. So, okay, so let's now go to the next question, and it is actually well motivated by this kind of situation. In business situation, we often talk about the same quantity, say cost, but it can be expressed guys, it's really hard to talk over some voices. I mean, really, really hard. I don't have naturally loud voice. You might have noticed, and to scream it's really, really hard. So please try to be quiet. Thanks. So the next part is actually quite motivated quite well by this kind of problem. In finance, we typically talk about some function, say cost function, but we may express it in terms of the quantity or in terms of price. And we can find the derivatives with respect to quantity or with respect to price. And it turns out that these derivatives are actually related. So I will start with kind of motivating the chain rule. Okay, so we might be given sometimes a function, say cost function, as a function of Q. And we might express the same function also as a function of price. And we might do this because we might be given some equation, demand equation. The price itself might be a function of Q. Well, and then we might talk about the following quantities. We might talk about the derivative of C with respect to Q, the usual marginal cost. Let me introduce a notation. We'll write dC over dQ. Well, that's just derivative of C relative to Q. You'll have this notation because, well, we want to distinguish, do we take derivative relative to quantity or relative to price? So we have different notations, and it's quite inconvenient to denote them by the same symbol, just prime. And that's about what, well, how C changes as Q increases by 1. We can also talk about this quantity, the derivative of cost relative to price. So if you express the cost as a function of price, you might still take the derivative here. And that's about how cost changes speed increases by 1. So as you increase the price by $1, this amount measures how much will the cost change. I'm not sure whether it will increase or decrease, so I say change. And another amount, dP by dQ, so derivative of this function. price as a function of quantity. So that's just the derivative of that function. And what is this about? Well, it's how price changes. Now I'm pretty sure it will decrease, but I'll say just changes as Q increases by 1. Well, we have all these quantities, and they are very naturally related. You can't have arbitrary 3 numbers. They are very much related. And the relation is very simple to understand. Suppose that I increase the quantity by 1. The cost will increase by that amount. Well, simultaneously, the price will get changed by that amount. So the price will decrease by dp by dq dollars. For each $1 of increase in price, the cost will change by that amount, dc by dp. That's what it is here. For each $1 of increase in price, at which we have dp by dq, we increase the price by dp by dq dollars. Well, that leads to a change of cost of that much. But we did the same thing. We just increased the quantity by 1 on both sides. So the change in cost, total change in cost, should be the same. So it turns out that if you express cost as a function of Q or as a function of P and find the derivatives, well, they're not exactly unrelated. They're related by this equation. In other words, if you take derivative of C relative to Q, well, we could have taken we could have expressed C in terms of P, which means we could have taken, okay, maybe I might be confusing with the prime. So let me read it like this. Well, this equation, we derived it, well, in particular application to finance. And we thought about this as being cost, this is quantity, this is price. But in fact, it is very general mathematical principle. It applies to just any functions, regardless of particular application. So in general, we have, let me start from here once again. The general chain rule. Not particular to any problem, just have this to always hold. Suppose you have a function g of q that you can also express in terms of x, which means you can write u as a function of x. And then you can express g as a function of x as well. So u is itself a function of x. Then you can write this function as a function of x. So like here we have the cost, quantity, and price. Here we have just more abstract things. Any function of u, and u is itself a function of something else, so I can express g as a function of this something else, of this x. Okay, and then it turns out that this relation, as it is written here, holds in general situation. What do I mean? If I want to find the derivative of this function expressed as function of x, so g of f of x, to find its derivative, turns out to be the same as to find the derivative relative to the previous variable u, g prime of u, times the derivative of dependence of u on x. So let me write down what the chain rule actually says, and we'll have some examples. So don't worry, this for now looks fast. So chain rule tells the following: g of f of x, derivative of such a thing can be computed like this. It's derivative of g evaluated at point f of x times derivative of f. And so, for this even to make sense, we should say that f is differentiable at x. This derivative must exist, and g is differentiable f of x. This derivative must exist. So it turns out that this equation holds for any two functions, well, with some small conditions, but basically always holds. Let's have an example, simple example. Let me compute what is the derivative of 1 of x cubed. Using this information, using this formula. Well, first of all, I will separate this process of computing 1 of x cubed to two steps. First I take x and compute x cubed. And then I take this result and I plug it into the function g, which is logarithm. So now 1 of x cubed is exactly g of f of x. Okay, so at least I know that we are in the situation where I want to compute the derivative of the composition. First apply one function, then apply another function. So that's about the left-hand side of this formula. Let's try the right-hand side. What is f prime at the point x? Well, 3x squared, nothing complicated. Derivative of x cubed is 3x squared. What is derivative of g? G prime of u is 1 over u. Well, it means that in this formula, so g prime at the point of x is 1 divided, and I should plug in u, which is equal to x cubed. And f prime of x is equal to 3x squared. Conclusion, well, if this formula is correct, and well, it is correct, the derivative of 1 of x cubed should be 1 over x cubed times 3x squared, which happens to be also 3 over x. we start with kind of very simple example, just composition of two functions. And well, the first time we do it kind of slowly. We understand what is one function, what is the other function, how they together form this expression, what are their derivatives, and how to plug these derivatives into this formula. So basically, each one of the steps is now on the board. And we get an answer. So maybe let me ask, how many of you find it very confusing? 2, 3, 4. How many of you find it confusing? Okay, another 5. Okay, I see. Okay, so we'll do one more example pretty slowly. But before this, I just wanted to confirm that we did got the right answer. Does anyone see a different way to compute this derivative? How? Okay, so my question is, I want to confirm that I got the right answer, that I didn't make any silly mistake. And the question is, can I find this derivative by some other method? How? Yes, exactly. I can rewrite 1 of x cubed is just 3 ln x. And then the derivative is the same as derivative of 3 ln x, which is 3 over s. Okay, so let me do another example, and maybe, okay, so let me do such an example. What is the derivative of sine of, well, let me use once again 1 of x. Find its derivative. So, actually it is written quite explicitly now as such a thing. So, this is exactly f, and this is g. So my f is now logarithm, and g is sine. So according to this formula, I should find g prime, the derivative of the outer function, the one that we applied last. What is derivative of sine? Cosine. Okay, so I should take derivative of this function g at the point at its argument. Its argument is 1 of x. Well, and then I should multiply by derivative of the inner function. So I should multiply by derivative of 1 of x. For now we write it like this. So that's exactly g prime at the point f of x, and this is exactly f prime of x. So I'm basically just separating this complicated function to first applying logarithm, then applying the sine. Okay, finally, I find what is derivative of logarithm, which is 1 over x. Well, unlike in this example, I don't have any other way to compute this derivative. So here, well, eventually we'll start just to read how this works in general. I mean, we explained a little bit why it works in some application. I told you that it works in general. Well, now you should know that it works in general and start learn how to apply it. Let's not erase it. Maybe I'll erase these conditions, but not the formula itself. Okay, so maybe questions, let's say, about this example. So in a way, here I just very slowly and accurately substituted my expressions for f and g in this formula, Well, eventually, basically in a couple of minutes, we'll start doing it much faster. So let's try more examples, and with each example, we'll do it faster and faster and faster. So let's compute. Let's compute let's do one simple example. Let's say cosine of 1 over x. Such a derivative. Let's understand here what are the functions. Well, to compute what is cosine of 1 over x, you do the following operation. You start with x, you compute 1 over x, first operation, and the second operation is compute cosine of the result. So my outer function, the last function that I apply, is cosine. So cosine is g in this formula, the last function to be applied. So in this formula, I should take g to be cosine. Well, what is derivative of cosine? Minus sine. Well, derivative of cosine is minus sine. So, and I should take minus sine of the same argument as it was here. So minus sine of 1 over x. And then I'm not done. I still have to multiply by derivative of the first function that we applied, which is 1 over x. So you should multiply by derivative of 1 over x. So it will be minus sine of 1 over x times minus 1 over x squared, or sine of 1 over x times x squared. Okay, so questions about this calculation. Once again, we are doing the same thing, but now we will eliminate one more step. We don't write explicitly what is f and g, we just keep it in our head. We see that first we apply f, then f which was 1 over x, and then we apply g which was cosine. Well, let's start doing more complicated stuff. Well, slightly more complicated stuff. What happens if you take derivative of square root of logarithm? Okay, so how can we find derivative of square root of logarithm? Once again, we should look whether it falls into this pattern, whether it is one function applied to another one. And yes, it is. To find this number, square root of ln of x, you first compute ln of x, and then you apply square root of the result. So my outer function, the function that I apply in the very last step, is taking the square root. What is the derivative of this operation, taking square root? 1 over 2 square roots. So derivative of square root is 1 over 2 square roots. Well, and I should take 1 over 2 square roots of the argument, which is 1 of x. And I'm not done yet. I still have to multiply by the derivative of the inner function, of the argument itself. So I should multiply the derivative of logarithm. Which is, of course, 1 over x. So basically, it should recognize when a function is a composition, when a function can be computed by doing a sequence of simple operations. Take x, compute logarithm of x, compute square root of the result. And then, well, in chain rule, we take the last operation, take its derivative at the point at which it was, the function was computed, and multiply by derivative of its argument. Okay. Let's try another one. Sine squared of x is derivative. So first we should understand what is this function about at all. What does it mean? So this function means that we take x, we compute its sine, and then we square the sine. So we square the result of applying sine. So an alternative way of writing this function is just sine of x squared. Okay, so now it is written in the form take x, compute sine, and then compute the square of the result. So which one is the last operation? Which is the outer function? Squaring, exactly. So last operation is squaring. What is the derivative of squaring? What is derivative of u squared? 2u, yes. So derivative of squaring is 2 times the argument. And the argument is sine of x. Well, but we are still not done. We have to multiply by the derivative of the argument itself. This part. So multiply by derivative of sine, which is cosine. Okay, so questions about this one? Well, let's try a slightly different one. What is the derivative of sine of x squared? Well, now, this is completely different function. It's not the same as this one. Here, we first... So here we first take x, we compute the sine, and then we find the square of the sine. Here we do quite these operations in quite the opposite order. We first take x, then compute square of x, and then find sine of the result. So what is the outer function here? Sine. Yes, so the last operation that we perform here is sine. So the first thing we'll write in the chain rule will be derivative of sine, which is cosine, of its argument. And then, once again, I'm not done, I have to multiply by derivative of the argument. So I get cosine of x squared times 2x. Well, naturally, you have different functions, you get different derivatives. Okay, so questions so far about these examples. So these examples, yeah,
What if you're doing something more difficult?
we will do something. Yes. I'm asking about, well, questions about simple examples. Just composition of two functions with explicit ones. Okay, so let's do indeed something slightly more difficult. Let's compute derivative of e to the power 5 sine of x squared. Well, now it looks a little bit more complicated. But actually it isn't really that more complicated. We still have a composition. We start with x, we compute x squared, we compute sine of the result, we multiply the result by 5, we compute e to the power of whatever we want. So which of these operations is the last one? The very last one, very last operation. Taking e to the power of the result. Okay, so the derivative will be as follows. It will be the derivative of e to some power, which is basically e to some power. So we take e to the power of the argument. That's the derivative of the outer function. So if this was just, well, u, then derivative e to power u would be just e to power u. But it isn't. This thing is itself a function. So we should multiply by the derivative of this thing, 5 sine of x squared. Well, we are not done yet. This is still a derivative of still complicated function. But we can of course compute it. We can write, first of all, we can take the 5 out. And then we'll have to compute derivative of sine of x squared. Well, how do we find this? So let me finally erase this. So we get e to the power of 5 sine of x squared times 5 times, well, here I have once again my last operation that I apply is sine of the argument. So derivative of sine is cosine. And I have to multiply by derivative of the argument. Well, and only now we're getting closer to getting the actual answer. So it's e to the power of 5 sine of x squared times 5 times cosine of x squared times 2x. So you see, even though the chain rule itself is pretty simple, you have, well, some formula, you recognize when you can apply it and apply it. But an expression could be complicated. It could be a composition of 5 functions. And each one of the functions could be a product of quotients of sums. And, well, then basically it becomes, the problem of computing the derivative becomes a chain of several computations. At each step, you recognize your expression as, let's say, a composition and apply the chain. Exactly what we did here. It's a composition of computing e to some power and computing what the power is. Well, the chain rule tells you you should take this last operation, find its derivative, and multiply by the derivative of the previous one. Repeat. Okay, so questions about this example? And maybe, well, a comment about style. You might be tempted, I mean, if you are performing long computation, you might be tempted to start skipping, repeating this factor, say, from the beginning to the end. Well, don't fall to this temptation. You should repeat it every time, and I mean, you just can't forget about it. I mean, if you do forget about it, and then realize that you will remember about it in the end, well, with chance of 50% you will not. So, do keep it. I mean, it's inconvenient, you have to write all formulas, but that's what you have to do. I mean, if you can do in your head all the computation from here to here, that's fine. But if you can't do it, and you say, you go from here to here, and then you start, well, and now kind of in your head you say, well, now derivative of this is this, and you forget to write this. And then you say, well, derivative of this is this, and you forget about all the stuff. And then you start combining them, then it becomes unclear. So you should do it always like this. Okay, questions? Yeah.
If you're doing something more difficult, x power of 5 over 2 plus 8, all brackets to negative 2.
So, can you say it again?
Okay, so all brackets, yeah, x to the power of 5 over 2, and then plus 8.
Plus what?
8.
8.
To the all bracket, negative 2. Yeah.
Well, to be honest, it's really not that complicated.
No, but the plus 8 is not inside the exponent.
Oh, I see. Plus 8. Okay. It's a reasonable example. I would still claim it's not really more complicated. So, basically, what happens in this example? We take, well, the last operation that we do is we take this result and raise it to power negative 2. Derivative of this operation raising something to negative 2. Derivative of u to negative 2 is negative 2 times this thing to power negative 3. So x to the power 5 halves plus 8 to power negative 3. So that's the derivative of the last operation, raising to power negative 2. And then we have to derive the previous operation, which was computing x to the power 5 halves plus 8. Find this derivative. Well, minus 2 times x to the power 5 halves plus 8 to negative 3 times, and here it's basically derivative, well, we have to apply the sum rule, which means it's the sum of this derivative plus derivative of 8, which is 0, and this derivative is 5 halves times x to the power 3 halves. So, in a way, it's even simpler than what we had before. There's only 2 steps. Okay, other questions? Okay, let me show you something, well, somewhat funny, I would say. Suppose you want to compute derivative of 2 to the power x. Well, it's definitely not given to me as a composition of 2 operations. It's just take 2 and raise it to power x. And that's it. One operation. But unfortunately, I don't know what is the derivative. I know, well, some related derivatives maybe. Derivative of e to the power x. But not this one. So, the idea here is maybe I can write it as e to some power. Does anyone have an idea how to write this as e to some power?
E to the power.
Oh. Yeah. So
E to the power.
my question is as follows. I want to find the derivative of 2 to the power x. Unfortunately, I don't know what it is. So my idea is to write it as maybe e to some power. Can I write 2 to the power x as e to some power? Well, in a way, I can write anything as e to some power. I can take any number. So before I go do this, I can take any number and write it as e to some power. Because e to the power 1 of z is z. Well, let me use it here. Let me write 2 to the power x as e to the power 1 of 2 to the power x. Well, this is good. I mean, now I have a function which looks like a composition, but one of the iterations in the composition is still this complicated one, 2 to the power x, of which I don't know what is the derivative. But I can rewrite this in a simpler way. How?
Log x over log 2.
Exactly. So e to the power x times ln 2. Okay, now it looks like a composition of very simple operations. Take x multiplied by ln 2, compute e to the power of the result. So now we can perform this computation very easily. Derivative of 2 to the power x is the same as derivative of e to the power x times ln 2. What is the last operation that we performed here? Well, it's raising e to the power of whatever is there. So derivative is e to that power. Well, times the derivative of the argument. Let me continue here. This is e to the power of x ln 2 times, what is the derivative of x times ln 2? X over 2? It's ln 2, yes. I mean, maybe since it caused confusion, let me discuss it. What is the derivative of 5x? Positive 5. What is derivative of 0.86x? Well, 0.886. What is derivative of ln 2 times x? Well, ln 2 happens to be about, well, 0.8. I don't know what it is exactly, but it is a number. It's not an operation that you do to x. It's just a number. So its derivative is just 1, 2. It's exactly the same kind of thing. Okay, finally, let's simplify this a little bit. We know that e to the power x ln 2 is exactly 2 to the power s. Okay, so you see that the chain rule is applicable even when it seems that it is not. So sometimes it helps you to find derivatives which don't look like a composition. You first make it look like a composition and then apply the chain rule. So last example for today. different kind. Suppose g at the point 5 is 3. And suppose g prime at the point 5 is 6. And suppose that h of x is 1 of g of x. What is the derivative of h at the point 5? So it's a slightly different kind of example in that I don't know what is g. I just know a little bit about it. I know its value and derivative at the point 5. And then I form such a function, logarithm of g of x. What is the derivative of this function? Almost 1 over g of x. Okay, yes, so let's compute it. So solution. Let's try to express derivative of h first at any point. Then we'll plug in x equal to 5. So h prime of x is the same as derivative of 1 of g of x. Now this looks like a composition. We take x, we compute g of x, and then we compute ln of the result. So the last function that we applied was logarithm. That's the outer function. Derivative of logarithm is 1 over its argument. So in this case, it's 1 over g of x. And then you should multiply by the inner derivative of the inner function, derivative of this argument, by g prime of x. Well, we can't go further from here, we can't simplify this expression, but we can plug in x equal to 5. So h prime of 5 is 1 divided by 3 times 6. Okay, so see you later today and good luck.
Questions? I'm going to turn this camera off. It's still recording. Say something. It's going to go on YouTube. I should turn it off.